which say the sum over all the operators in the landmark has to be more than 1 for every landmark that you know about, and flow conservation constraints, which basically say that the number of times that you produce something, subtract the number of times you consume something, has to be within some range based on whether it's in the initial state or the goal state or not. So when we solve one of these, yes, we get a heuristic estimate, but we also get an assignment to these YO variables. And normally when you're doing operations research, which is the main field that makes use of LPs and MIPS, the last thing you actually care about is the objective function. What you really care about is that assignment. And this work is really about trying to work out how we exploit that information and the things that we can do with it. So, yes, okay, my slides are working. So if we end up with an operator count, there are some things we can do with it. So I've got a running example for these. And this is a very simplified version of gripper. So you have 2 balls, B1 and B2. I've just condensed them here into BI, but there's 2 of those. You've got to move them from the left room into the right room. So the robot starts in the left room and can move right or move left, and both of those states are consistent with the goal. Each ball has to go from the left room into the gripper into the right room, and the goal is achieved only when they're both in the right room. And the gripper itself, which we have 1 of, can either be empty or non-empty. And so here we have an operator count. It's not necessarily come from any specific heuristic, but I promise it is admissible. It is a lower bound on what we actually need to do, as in the cost is a lower bound. And we can look at this as humans, and we can see that there's something wrong with it. And the conjecture that I'm going to ask you to believe for the next few slides is that whenever we have an operator count, either it is the projection of a plan, i.e. there is a plan which has exactly that set of operators, or there isn't, and there's a reason why not. Now in this example, we think we can pick up the first ball in the left-hand room, pick up the second ball in the left-hand room, move to the right, drop those balls, both of them, move left, and we're done. Now I know looking at this that if I'm moving these one at a time and there are 2 balls, I have to move right twice. And so we can say, we notice that there is a flaw in this operator count, and it's here. And what I'm going to ask you to believe for the time being is that there is always a flaw of this kind if it isn't a projection of operator count. It might be disjunctive. And the word disjunctive is important here, because the way that we're going to explain these flaws is based on a generalization of disjunctive action landmarks. Sorry, I missed a bit. So we can fix that by changing that into 2. Once it's 2, we have an optimal plan. So we pick up the first ball, we move right, we drop the first ball, we move left again, we pick up the second ball, we move right, we drop it, and that can be sequenced into a plan. So yeah, disjunctive action landmarks. This is what we're going to generalize into something that we can explain all of these flaws with. So a disjunctive action landmark, the simplest version, and this is how it tends to get encoded in an operator counting heuristic, is just saying that the sum over all of these has to be greater than 1. I need at least 1 of them. And if you have a MIP, that forces you to choose exactly 1 of them, or possibly more than 1, but you have to do a whole of one of those actions. If it's an LP, you might be doing fractions of them, but for now we'll assume that we're solving mixed integer versions of these operator counting heuristics. So another way of writing that down is in terms of what we're calling bounds literals. So this is basically saying so these square brackets define a new 0, 1 variable that takes the value 1 if and only if the logical statement inside it is true. So either we have 1 of y1, or we have 1 of y2, or we have 1 of y3, and so on. These 2 are semantically equivalent. And yeah, in English, at least one of these operators occurs at least once. So we generalize that. So basically, instead of having 1 here, we have k. I've gone too far somehow. Yes, here we are. And potentially different k's for different operators. And this is what allows us to be very, very expressive in what we disallow. So this is saying, we have k1 of y1, or we have kn of yn, and so on. And so the flaw that we identified earlier can be expressed like this. We need at least 2 of move right. Now, unfortunately, these bounds literals are not baked into MIPS. We need to add a lot of constraints. Well, 3 constraints per bounds literal to make them work. Unfortunately, we're not using CP for the master problem. These things kind of come for free if you're using CP. but you end up with integer problems and it's NP hard. So it's easy enough to encode constraints in an MIP to actually make these things behave. So this first constraint basically says if we're greater than k, then obviously we're greater than k minus 1. That's just, if I have 3 of an operator, then I also have at least 2 of that operator. The second constraint says that if I've set k bounds literals, so I've set 1, 2, and 3, then I must have at least 3 operators. I could have more, but I have to have at least 3. And the third one is the tricky one that you should probably read the paper to work out exactly how that works. Uses big M tricks. Basically, this is a very large number, and it says that if I have set the kth bound literal, I'd better have at least k, if I have k of these, then I'd better have set the kth bounds literal. And then we lazily generate these literals and these constraints, because obviously you can have a lot of one operator in a plan. You don't want to create all of these a priori because your MIP will explode. But unless they're mentioned in a generalized landmark, you don't need them. Oops. So I'm going to sort of first give a little bit of a corollary of that conjecture I asked you to believe earlier. Basically the idea that either we can find a plan with exactly a specific operator count, or there's something wrong with that operator count. And that means that using just these generalized bound literals, we can characterize H star. So how we prove that is exactly using the kind of method that we said before. You can always add a specific flaw, and there's a trivial flaw, which I'll explain in a second. So because the MIP is a admissible heuristic, the optimal solution to it is a lower bound on the cost. So if we can sequence it, we've proved optimality, because it has a cost equal to the lower bound that we obtained from the heuristic. But also, if we can't sequence that into a plan at all, then we know that you can always say, I need one more of something. I don't know necessarily what that something is, but I need one more of it, because I know I can't sequence any strict subset, because otherwise that would be the MIP optimum. So we've already got a proof that you can't sequence any strict subset, so we say I need one more of something. And I might be swapping that out for something else, but I need something different, something I didn't have before. And that's a trivial explanation that always applies if the answer to can I sequence this is no. And so this gives us, so if you iterate this, you're guaranteed to find a plan eventually, because there's only finitely many distinct operator counts, which are compatible with an upper bound on the length of the optimal plan. So this gives us kind of a fundamentally new algorithm for doing planning, and it's based on logic-based Bender's decomposition. The idea being you solve the MIP, you get an operator count, and that maps every operator to the number of occurrences, a natural number. You send that to a sequencing problem. We happen to use SAT, but in theory you could use anything that can explain its inferences. And what happens is these send these generalized landmarks back, and hopefully it's a subset of the total operators. So there's some inconsistent subset that mean that I can't sequence it. I don't have enough of one of these small set of actions. So talking about SAT, this is kind of the key to why this works. You can think of this as a cost-optimal SAT plan as well, if you like. How we do that is we encode at most k constraints. So we create this layered SAT encoding, just like most SAT planners. So if we get an operator count that says we need 15 actions, we generate 15 layers, and we encode extra constraints that say, well, this action A, was chosen only once in our set, so we create a counting constraint along all the layers saying, over all the layers, I can only choose this once. And we add these as assumptions into the SAT model. The way that SAT solvers work is that they build an implication graph. And what they work out is for every, whenever they make a decision, and you just force the first few decisions to be your assumptions, we will remember why any of their propagations, any of the conflicts that occur happen. And so if it comes back as false in all conflict-directed clause learning solvers, which is pretty much everything that is made nowadays, they can always rewrite their failure in terms of some subset of the assumptions. And usually it's a strict subset, which is a property we really want. So these aren't great, these aren't perfect cuts, but we can see the difference here between, this is the naive cut. This is just, I need one more of something. And what the SAT solver allows us to do is it effectively collapses these 4 red ones into this fake action, I need one more. And the reason that we need this is basically because the no good that we get out of our SAT is only true for the current formula length. If we add another layer to the formula, that no good might not be true anymore. So we say, oops, we say, I need one more of these actions which occurred in my no good, or I need a longer formula. And so, yeah, this is a strictly stronger cut than this one because, well, if you have a longer formula, you necessarily have one more of something. So what's really cool about this is sort of a tangential result that we got, but is really interesting, is we've kind of proved that the hard, maybe this is unsurprising to some of you, but the hard part of planning is choosing what to do, not what order to do it in. So here we have the so we ran these over the 2011 benchmarks, just trying to solve planning tasks by solve the heuristic, try and sequence it. If it says no, add a new constraint to the MIP, repeat. And so we collected about 1 million or so sequence calls, and the vast majority of them happen in a tiny fraction of a second. So this is disproving the existence of any sequence given a set of operators. That feels like that should be a factorial operation, because you've got to try a bunch of sequences. But in practice, it's incredibly fast. And 99% of them took less than a second. And in work we've done since, we've actually brought that tail in a little bit more. So these are coverage results. Basically, we're solving things at the root here with no forward search at all. And we solve a significant proportion of the 2011 benchmarks. So this can be thought of as kind of a super heuristic. So we compare it with HPP, the incremental lower bounding solver, and it does a hell of a lot better. Basically because we can start with these really powerful operator counting heuristics as the starting point. Obviously, sim-based star is magic, but this is a very new approach to planning. These are preliminary results, and we're reasonably happy with that. And those numbers have gone up in work we've done since. So yeah, what I'd like you to take home from this is that this is a fundamentally new approach to planning based on logic-based Bendis decomposition, and it separates the problem into 2 halves: choosing what to do and choosing what order in which to do it. And what we're really excited about is the future of this by adding different constraints into the subproblem. Any existing SMT theory, potentially, can be added into the subproblem, and we effectively learn a heuristic that encodes incrementally the conflicts that occur because of that numeric constraint, for example, or a temporal network constraint. And yeah, basically we can use the theories and the constraints that have been built by the CP and SMT communities, hopefully, to do something resembling planning modulo theories. And yeah, so we hope to be able to tackle temporal planning and important planning with resources, and really both of those together, these kind of hybrid planning scheduling problems. Because a lot of real-world scheduling problems have these kind of, I don't really know what I'm supposed to do yet questions. Thank you.